So this week, our essential question is, why do things float? And this has to do with the principle of buoyancy. I'm just going to hop over to a PowerPoint that I have. And this takes us, give you a little history lesson, on a fellow by the name of Archimedes. And basically, to make a long story short, Archimedes was the smart guy in the village, and the king wanted to know if his crown was really made of gold. So he charged Archimedes with solving the problem, is my crown made of gold? And at first the problem vexed Archimedes, so he thought about it, and one day, sitting in the bathtub, when he got in, he noticed that the water level rose up, and so therefore he displaced some water, and it must have triggered something in his mind, and he yelled, "Eureka, Eureka, I found it, I figured it out." And apparently he ran around the town naked because he was so happy that he figured out the solution to the problem, how he was going to figure out if the crown was made of gold. Okay, so there's a song somewhere on that I'll have to find, and maybe I can play it for you. So let's go over to your book questions for EQ3. That would have been 12.6 that you would have found over here in your book readings, hopefully you've done that by now. Okay, so buoyant force is a force that fluids exert on any object that is placed in them. And I'll explain that in a little bit more detail and get away from the book language. Number two, what explains buoyant force? So a fluid exerts pressure in all directions, but the pressure is greater at a deeper depth. And you probably experienced that if you swim in the pool or a quarry or a lake where you could dive down more than 4 feet. But even if you dove to 6 feet, you probably felt that in your ears. Number three, the fluid below an object, where the fluid is deeper, exerts greater pressure on that object than the fluid above it. So you were to sketch force arrows on here, which is going to be a little hard for me to do right here, but if you take a look in the book, you will notice that you have your force arrows below are greater than up on top. Right, and we talked about vectors way back in January. Okay, let's talk about weight and buoyant force. Okay, so we know that weight, this is number 4, is a measure of the force of gravity. That's review. We've talked about that before. We know that acts in a downward, in our frame of reference, that acts down towards the center of the earth. Okay, so we know that buoyant force acts upwards on an object, or we would say counter to gravity. Okay? So, which force is greater determines if something is going to float or sink. So let's take a look here at number 7. This was a sketch that you had to do from your textbook. Draw and label buoyant force arrows and weight arrows for both objects and explain why one floats and the other sinks. So if you take a look, this object is floating. So we know that the weight arrow, which is acting downwards, is going to be equal as the buoyant force arrows acting upwards. So those forces are in balance. On this object, the orange object on the right, we can see that the object is sinking. What that means is the weight arrow, force of gravity, is going to be a longer arrow. It's going to be greater than what buoyant force is. Okay. So that was 8 and 9. And then number 10, you had to launch the interactive to explore how density affects buoyancy. I'm going to hop back over to my trusty old PowerPoint. And I wanted to show you some things here. Okay. So here you had to compare the buoyant force in container A with the buoyant force in container B. So if you need to, just pause and think about that for a moment. Okay, so what you get is object A is floating. That means buoyant force and weight are equal. The forces are balanced. In container B, weight is going to be greater than buoyant force because the object has sunk. And if there's no bottom here, it would keep on sinking. Okay. Okay. I wanted to show you something else. Yeah. Right here. Okay. So another little graphic. So here we have a cnidarian, or jellyfish, floating. We could see that the force arrows are balanced. Here we have a turtle, which is not on top of the surface, but the forces are still balanced, weight and buoyant force. So he's floating, but maybe not on top. And then we look over here at the crustacean, and what we have here is he's on the bottom, therefore your vector acting downwards, which is weight, is going to be greater than buoyant force. Okay, so hopefully at this point you got the idea here. And this is the kind of the simple part of this whole thing called buoyancy. Where things get a little tricky, and this is something that we would normally have done in a lab, and this gets back to where Archimedes figured a couple things out. Okay. What he said is that the buoyant force acting on a submerged object is equal to the weight of the fluid that the object displaces. So imagine here for a moment, you put this canister, this is an old film canister, back before we had digital cameras. You submerge this inside of here. Well, this water, it's going to displace water. Well, if we capture that water into this beaker right here, what we would do is we would weigh just this water. Whatever the weight of this water is, that is exactly equal to the buoyant force. You see? So the weight of this represents the buoyant force that's pushing up. And in this case, this is greater than the weight of the can. I'm sorry, the other way around. Let me rephrase that. Because the can has sunk, the weight is greater, the weight of the can is greater than the weight of the displaced fluid. So back to the slide. So in this particular container, here we see that the film can is floating. So we definitely know that there's a buoyant force acting on that. In this case, we know that the buoyant force and the weight are equal. But this canister inside the beaker is still displacing a certain amount of water. How much that displaced is exactly equal to the buoyant force acting upwards on that can. So here's a really simple diagram. We have an overflow container, we have a mass that's going to be lowered in, say a weight. So you see that the weight is 7 pounds. Archimedes' principle states the buoyant force is equal to the weight of the displaced water. The weight is lowered into the water. We now know that the weight has gone from 7 to 4. Right? We know that that is a 3-pound difference, and that's the buoyant force. That is also the amount of the weight of the water that has come out and has been collected. Okay, so let's take a look at some of these questions. These are actual open-ended test questions that we would normally give. So let's take a look here. It says, when the block was placed in the liquid in container A, the level of the liquid rose. Okay, so we would say that the block displaced some of the fluid. Number 8. They're going to gradually get a little bit more complicated. In what direction is the buoyant force acting on the block in container A? You can hit pause, think about that for a moment. We know that the buoyant force is acting upwards on that block of wood in container A. Let's take a look at number 9. How is the buoyant force related to the displaced liquid in container A? And this one is going to be a little bit more complicated. So you might want to hit pause and figure this one out momentarily, and then push play when you are ready. Okay, so back to this question. So how is the buoyant force related to the displaced liquid in container A? The weight of the displaced liquid equals the buoyant force on the block. Okay, so we go to number 10. Compare the buoyant force on the block in container B with the weight of the block. So if you said that the buoyant force is less than the weight of the block, you were right. Here's the explanation. The buoyant force acts upwards and the weight of the blocks acts downwards. Because the weight is greater than the buoyant force, the block sinks. Okay, kind of wordy, I know. Let's go to the next one. Get ready for this. Compare the buoyant force in container A with the buoyant force in container B. What I'm asking, which one's greater? Is buoyant force greater acting in A, or is the buoyant force greater acting on the block in container B? Now, to answer that question, remember what buoyant force is equal to. It's equal to the amount of water displaced. So you have to compare how much water was displaced when block A was put into container A versus B, right? So you know that if you were to take this block and push down on it, more water, the water level would rise, right? Okay? And that's what's happening here with block B. It is completely submerged. So is it A or B? Which one's going to displace more water? And whichever block is going to displace more water, that has the greatest buoyant force. Here's the tricky part. People think that the buoyant force is greater in A because it's floating. But that's not true. Okay? Now remember what Archimedes' principle states, that buoyant force equals weight of the fluid displaced by the object.